Okay, so just picking up here. So the Pythagorean identity, there's 3 of them, like I said. This one we're going to use like every day, okay? And I'm going to show it to you more in depth down here, okay? So Pythagorean identity, you hear that word Pythagorean in there, and you might remember Pythagorean as a squared plus b squared equals c squared. It has to do with a right triangle, the sides of a right triangle. And remember, the unit circle is made up of a whole bunch of right triangles. So let's look at a quadrant 1 right triangle on the unit circle. And we always make, start at the origin, go out to the circle, drop to the x-axis to make our right angle, and theta is always at the origin. How we draw our right triangles, right? And we can look at a right triangle and call it so many different things, right? Back in geometry, even in this class, we'd say a squared plus b squared equals c squared. We have done x squared plus y squared equals radius squared. Knowing what the legs are versus the hypotenuse, let's talk about the different parts of this. This is a point on the unit circle. In algebra, we would call it xy. Trig, we'd call it cosine x, sine x. And let me get this out of the way real quick. You can use x, you can use theta, you can use y, you can use z, you can use beta, gamma, sigma. Any letter in the English alphabet, the Greek alphabet, you will see written there. Theta and x are the most common. And if you want to change it in the middle of a problem, you'll see me doing that sometimes. It might say theta at, in the given problem, and I might write x. It doesn't matter. It's a variable. Okay, so that doesn't matter. All right, so this point is x, y, or cosine, sine. And so where this first Pythagorean identity comes from, which is that one we have up there, and I'm going to write it backwards. Oh my gosh. Not really backwards. I'm rewriting this. These mean the same thing, right? Addition, order, doesn't matter as long as your 2 legs are on the left-hand side. That's coming from the fact that this is cosine, your x, right? And this would be sine. So those are your 2 legs of a right triangle. So when you do this side squared plus this side squared, where are they getting 1 from? 1 is your radius, and 1 is the radius, hypotenuse of all of the right triangles on the unit circle. That's where the word unit comes from, 1. Okay, so that's where this comes from. The basic Pythagorean theorem just written in trig language. Okay, now you are going to see this trig identity written 2 other ways. Let me show you what they are. Go ahead and write them, and then we'll talk about where it came from. Although, sure, if you take a quick second and look at it, you'll see where they come from. So in an equation, you can isolate different parts of it, right? Isolate, get it by itself. Like in the given one, 1 is by itself. The cosine and sine are on the other side. Here in the second one, all I did was subtract sine squared x from both sides, right? To isolate the cosine squared x. Here, I isolated the sine squared x by subtracting cosine squared x, okay? So these all mean the same thing. You can write them. You can be given cosine squared x, and you might rewrite it like that. This will make more sense when I keep talking about this rewriting. But you can substitute in a left side of an equation for a right side of the equation with any of these identities, okay? And that's what we have to learn how to do, is we're going to be looking at some problems and having to rewrite parts of them, okay? So one thing I want you to just take away for a minute is when you see, because you're going to have to start recognizing things. When do I use this one? How am I going to know when to use which one? One of the things I want you to pick up on is all 3 of these involved the trig function sine, cosine, trig function squared, right? They're always squared. And there's 1s involved and a plus or a minus, okay? That should stand out to you. And I'll keep bringing that up when we get to some other problems here in a second. Now, we have to skip around a little bit, so you have to bear with me. Part of our notes is our homework. All right, so we're going to page 144, so I can finally show you the first type of 2 problems that we're doing. So page 144 is where we're going to go. And right now, as part of the notes, I'm going to show you exactly why I just showed you that by going through 1 through 6. Okay? So what I want you guys to look at here is we have some expressions. So think about what expression means. It's not an equation where there's an equal sign. It's like 4x over x squared. That's an expression. 3/12. That's an expression. Okay? And we are going to simplify it down to as small as we can. We're going to try and get rid of any pluses or minuses. We're going to, if there's multiple trig functions in the problem, we're going to get down to 1. You might even get down to just a number sometimes. That number is usually 1, but you'll see. Okay? So what you're going to have to do is look at the problem and think which one or ones of my identities applies to what I'm looking at here. And so one of the reasons I just told you guys to start recognizing pluses, minuses, ones, and squareds is what you should hopefully see is that this is one of your Pythagorean identities. You will get more comfortable with these the more you see them. Oops, I keep doing that. I can't stand it when I do that. I make the same mistake again and again. So cosine squared x plus sine squared x equals 1. That's one of the identities. If you know that one, you should be able to find the other two without doing any fancy work, okay? So when I look at this, I can say, oh yeah, isn't it this same one with, you don't have to do this really good. Oops, I did the opposite one, right? If it was cosine squared x here, it'd be 1 minus sine x on that side. So my denominator right here, not doing anything to my numerator, I'm going to change my denominator to what? After I just confused you. What am I going to change it to? Let me try again. There's the original one. And if I isolate the cosine squared, that's what we just did on that other page, I would get cosine squared x equals 1 minus sine squared x. Do you have to do that work just to know that? I don't think so. Again, if you know the original equation, you just can see if I subtract sine squared x from both sides, I would have 1 minus sine squared x. 1 minus sine squared x is the same as cosine squared x. Okay? Anybody have an algebraic idea of a way we could simplify that? Sometimes, okay, I have lots of little analogies and kind of silly things I say to help you guys remember things. One of them is when you're looking at doing math with words, think about it. Back in elementary school, you learned how to add and subtract, count on your fingers, blocks, whatever they do at that age. And then in middle school-ish, you started putting letters in the math. And now we're doing math with words. It's math with words. In other words, if I had y over y squared, that's algebraic, would you guys know how to simplify that? Yeah. You can cancel a y on top with a y on the bottom because cosine squared x just means cosine times cosine. That's 2 cosines. So you could write it like that if you wanted to. So I'll go ahead and write this, but you don't have to. But maybe in case I'm losing any of you, I'm going to write it like that. Right? That's what, that in green is what is in blue. That means the same thing. And when you see it like that, maybe it's easier for you to say, okay, I can cancel 1 on top with 1 on the bottom. That would leave me with 1 on top over cosine x. Is there any way I can simplify that further? Like, in other words, if I had 8 over 4, would I leave it as 8 over 4? I would write it as 2, right? We would never leave that. If I can make this fraction any simpler, I would. What can I write 1 over cosine as? Secant, right, Jordan? Secant x or whatever. So that guy simplified gets you to that. So that's that reciprocal identity. The flips are the friends. Now, say it again. Yes, yes, inverse, yes, yeah. Arc, she's flipping. Actually, no, that's when it's an angle that you're trying to find. No, this is just this. 1 over cosine equals secant, okay? So if you're not feeling sure of yourself, you're in very good company. It is very normal. This is going to take some time, even for you smarties, to get comfortable with this, okay? It is very, very normal, so just stay with me. It's going to take many, many encounters, lots of touching, playing with, trying, erroring, trying again to get these. It's normal, okay? All right, look at this next one. Again, do you notice, just like we had in this one, I see pluses or minuses, ones, and trig functions squared. This probably has to do with my trig identities, and it does. What does that numerator equal? Now that we talked about it at length in the last one, what does that numerator equal? What's another way you could write that numerator? Sine squared x theta, whatever variable you want, okay? So I'll stick with theta. So that's sine squared theta. Okay, that's my numerator for this reason right here. 1 minus cosine squared theta equals sine squared. What does my denominator equal? Yeah. See, that came a little bit quicker for you guys. The more you deal with them, the easier it becomes. Okay? This is new for all of you. All right? Now, is there anything else I can do? Is there a way to not have this be in fraction form, for example? Is there a way to make this a single term? Answer is yes. If you know that sine over cosine equals tan, what do you think sine squared over cosine squared equals? Tan squared. Yes. And that's as far as we can go. We're down to just one term. Okay? So in 1 and 2, we had pluses and minuses and squared stuff. Kind of think about that again in the future when you see those Pythagorean identities. Okay? Look at the last three we're going to do here. These don't have pluses, they don't have minuses, they don't have squareds. I talk about working in this section 3.12. I call it, we're all wearing a trig tool belt. Picture it. You're wearing a trig tool belt, and you have different tricks in there, and you try to find that tool, that trick that's going to work on each problem. And you're going to learn more tomorrow, okay? But the second trick today, the first one was looking for the Pythagorean identities. The second one I'm going to teach, which is actually the most common thing to do, is change everything to sine and cosine. If you look at it and you can change anything to sine or cosine, that's what you want to start with, typically, okay? And you'll see why as we work on these more. It's because they're the most commonly used ones. So when you're changing everything to sine and cosine, it gives you more options of ways to simplify, okay? So cotan, opposite of tan, cotan, I can change that to cosine over sine. If you need to use your identity sheet in the beginning, you can, but just know you do need to know these. So I just used this one right here. Okay, so all I did was change that cotan to cosine over sine. And when you see those next to each other, it means multiplication. So I'm just putting a times symbol there. Okay. Anybody see something algebraically? Think of what you know in algebra. Same thing works for words. The signs cancel, yeah. Because it's multiplication, you can do that. This is like a over 1 if you needed to see that. As long as it's not a plus or a minus there, you can cancel anything on top with anything on the bottom. So the signs cancel, you're left with cosine x over 1 or just cosine x. Nice and simple. See how they're using y here? It looks funny to me. I don't like using that letter. All right, again, I don't know. These are pretty basic, believe it or not. It'll become clearer to you to change things to sine and cosine. Because really, what else are you going to do? What else can I do with cosine? Actually, there's 2 different ways we could do this problem. I'll show you both real quick. It's just 2 steps. So cosine is cosine, right? Secant is 1 over what? Cosine. And don't those 2 cancel? Bye. Not with 1. But couldn't I have done it the other way around? Let me just show you. And that's totally fine. I could change cosine to 1 over secant. Still get the same answer. That's what makes grading these the worst part of my entire year, is grading trig verification quizzes, because I have to check every single one of your steps, because there's not just one way of doing these. And all the time I have students say, well, I saw it like this. I'll be like, oh my gosh, I didn't see that. That would have been so much easier. Okay, so always feel free to share. But yeah, either way would have been fine. As long as you follow the rules, there's more than one path to get to that answer. And so I'm guessing we can figure out what we do to start this problem here, right? Arlen, come on. Tan is sine over cosine. Don't need to do anything to cosine. What? You're talking to him? Okay. I thought I made a mistake. You doing okay, Ty? Starting to go? It's okay if you're not getting this, okay? It's really, really normal. We got to go back to the next page of our notes, though, to show you what, this is just to get you warmed up. These are not really what your problems are going to be like, typically. Carla, is it coming back to you a little bit? A little bit? We're going to have a divide in this room for real with all my students. There's going to be people that are like, these are so fun, I get it. And some people are like, I hate them, okay? That's just, it's kind of like anything else, but I hear it the most with these. Okay, here's the actual proofs. These are the rules, okay? You're given an equivalent statement. This is an equation. The left side does, in fact, equal the right side. We have to prove why. Why is that a true statement, okay? And to do that, you pick a side to work with, and you only work with that side. So that's one important rule. You never go on either side. You pick one side. And there are some problems where it doesn't matter which side, but here's how to make a decision. Pick the side that has more happening on it, the more quote-unquote complicated, because that means you have more to work with, okay? So when I look at this problem, I'm going to choose to work with the left-hand side because there's more to work with, okay? And the problems we just had look just like that. You just had to simplify it. Well, now it's almost easier if you think about it. What we're trying to do is make this side look like that side. So we have a hint of what is supposed to happen. So again, this is beta. This is the letter B in the Greek alphabet. Use it or use another letter. It's up to you. And I'm going to use that first or second trick I taught you, which is change everything to sine and cosine. It's a great starting place when you don't know what else to do, okay? So cosine times sine over cosine. And watch, I'm just going to put an equal sign here, but I'm not going to write that right-hand side. It's not wrong if you do. There's just no need to. You kind of focus on one side only, and then in our last step, we'll write the left side equals the right side. Okay, so just stay with me for a second. I think you all know what we should do with this right here is cancel the cosines, right? And look, sine x equals sine x. So this is a little baby one, and you'll see me put like a little squiggle there just to show I carried it down, okay? So I just proved that that side equals that side, all right? Left side or right side in this example? Left, right? There's more to work with. So changing everything to sine and cosine, secant would be 1 over cosine. And this is multiplication, so I can multiply them together without a common denominator. Remember, whatever applies in numbers and variables applies with words. So I can multiply 1 times cosine in my denominator, no problem. That gives me sine x over cosine x. And we know that that equals tan x. Okay? So those were the easiest level, okay? Got you warmed up. All right? Okay. Now, here's where we start getting a little bit more in depth. If you look at this one, what we're trying to do is make this crazy looking fraction with these weird letters in it, words, equal this. This one has squared in it. This one has a fraction in it. What is going on? So I want you to look at that and think, this looks impossible. I almost want you to. I don't really want you to. But because another one of my silly analogies is a forest. You know when you go to a forest, you do it all the time, right? You go to a forest and it's really thick, dense trees. And you need to get to the other side. and you have to figure out how to get to the other side. But it's so dense, you can't predict, you can't like mark a path out, okay? So what do? You take a step, okay? And when you take one step, that leads you to a second step. And sometimes you're like, oh, and then you can run because you can see the other side nice and clearly. Sometimes you're like, I still don't know where I am. I don't know where the path is going. I'm going to have to back up, start over again, and find a different path. It happens all the time. You have to be okay with making mistakes, and you want to probably start using pencil if possible when we get to like when you're working on your own, okay? Now, one of the things that we can do is do something called decomposing fractions, meaning taking one that's written as one big fat fraction and breaking it into two. Because I can see we're broken into like a binomial over here with no denominator. So I may not be able to predict what's going to happen next, but I know I can do that. I'm going to show you how. It's very uncomfortable because you guys are excellent math students. And without solving this equation, you could tell me the steps. You could tell me how to start it, how to end it. I could make this even more complicated with parentheses. You could say, oh, I would do the distributive property, combine like, you could say all the right words and explain it to me. You can't with these, or I can't, and I'm good at them, all right? You have to do one thing at a time and be okay with that, and some of us don't like that. All right, so I have subtraction in my numerator over a common denominator. Let's bust this up into two separate fractions. It's like sine x over cosecant x minus cosecant x over cosecant x. Okay? Now, you're going to also hear me and see me do this little backwards arrow thing. When I write that, what I'm saying to you, or I'm showing you in my notes, is sometimes it's really hard to go from the big fat fraction to the two separate fractions. So when I write that, I'm showing you that I checked it in reverse. If I start here and I wanted to combine it into one big fat fraction, I need a common denominator. Okay, I have that. So that would be the denominator, and I would just subtract my numerator. So sometimes checking in reverse is really helpful to make sure you separated your fraction correctly. All right, I still don't know how I'm going to make this, but you're going to keep your eye on that right-hand side because that's your goal. You don't want to just willy-nilly just start doing crazy things. Always glance over there. My eyes are constantly glancing over there. And I just caught something. What's cosecant over cosecant? 1, and that's what we want. So I might be on the right track, okay? That would make me feel a little encouraged on a problem like this. All right, I somehow have to make sine x over cosecant x into sine squared x. Okay, all I really know I can do is, let's separate it. I'm separating a fraction again. Now, look at what just happened. What's completely different in that fraction from the one above it. It's multiplication, right? It's just sine on top and cosecant on the bottom. When I separated it, it's check it in reverse because it's different from multiplication than when it was subtraction. If I multiplied those two together, I would get that, right? And then, oh, what if what? Does anyone see it? I don't want to just tell you, Jordan. Change what to sign? You can't just say change it to sign. I feel like you guys are starting to see it, okay, which is awesome. Good job. I heard someone over here say it too. So 1 over cosecant is sine. Remember, you're looking over here. Somehow I have to get a sine times sine to get a sine squared. And now, finally, I can see the path through the trees, right? I'm there. Maybe you were there 20 minutes ago. But sine squared x minus 1 equals sine squared x minus 1. See how I only have to write it that last time? There's no reason. You can. It's not wrong to. If it helps you, feel free to do that. But you don't need to. This is kind of the typical way of doing it. Okay? Okay, I think we have a little bit more. I already taught you this trick. Notes are kind of out of order. Changing everything to sine and cosine. One of the reasons I know that that's happening here, think about, so I like to say, this is what I see to kind of share with you how I attack the problem. I'm going to start with the left-hand side because there's more going on the left-hand side. And by the way, I didn't have that conversation with you up here. There might have been a way of doing it with this one too. You might have been able to start with either side. Okay, there are some problems that you could do the left side or the right side. It doesn't matter. Pick a side though. You never work on both sides. Okay, so I'm going to start with the left-hand side, and I need to change this to down to one term. Okay, this is really sine times secant times cosecant. So it's really like 4 things. I have to make it down to 1. This is a great opportunity to use our tool of changing everything to sine and cosine. Okay, so sine squared secant is 1 over cosine. Cosecant is 1 over sine. Okay, remember, sine squared is 2 sines. If it helps you to put a 1 under it to kind of keep your placeholder, feel free. But since everything's multiplied, you can cancel stuff on top with stuff on the bottom. Okay? Diagonal, anywhere, just not side to side. So I can cancel this sine x with 1 of those sines, right? Because it was 2. So now I have sine x times 1 on top. Okay, that's sine x. 1 times cosine x on the bottom. Multiplication, I don't need a common denominator. And keeping my eye on the prize, sine over cosine is tan. Are they getting a little easier? It's okay if not. We're all at our own speeds. Okay? 1 more here, 1 more on the homework page, and you're done for today, okay? So I have to add together these 3 words and make it into this word. They're not even the same words. It seems hard, and that's okay. Do one thing. Do one thing, and that usually leads you to another thing, okay? One thing I know to do is what? What can I do? That's right. Okay? It's normal. It's what happens to me. It is 100% normal to not know what the next step is. We're not making a whole plan. We're doing 1 step at a time. So that's sine x times sine over cosine. And then there's a plus sign, cosine x. Right? Okay. Well, what I can do is, so I just made these 2 terms into these 2 terms. I can make it into 1 term, right? I can combine these 2. That would be sine squared x over cosine x. And how do I know to do that? Well, I'm the teacher. But I'm keeping my eye on the right-hand side. There's no pluses or minuses over there. I know that I have to go from adding to actually adding them together and getting them into 1. So we kind of went from, they're 2 terms, it's a binomial, but I'm slowly getting down to 1 term. I want to add these 2 together. If I want to add 2 fractions, what's the rule that we learned in 3rd grade? Common denominator. You didn't have to have it for multiplication, but you have to have it for addition. Like if I had 1/4 plus 3 over 1, my common denominator would be 4, right? And I would multiply this fraction, the bottom and the top, by 4. Same concept, just with words. What's my common denominator for these 2? Cosine, right? So I don't need to do anything to this fraction. It already has that denominator. I have to multiply this guy's denominator by cosine x and his numerator by cosine x. Remember, you can do anything you want to a fraction as long as you do it to both the bottom and the top. So now I have cosine x as my common denominator, and I have sine squared x plus cosine x times cosine x, cosine squared x. Oh, she said something about squareds. What does sine squared x plus cosine squared x equal? 1. It's your very original Pythagorean identity. You're going to see it a lot. What's fabulous about that identity is you take this mess, sine squared x plus cosine squared x, or the other way around, and it just simplifies right down to 1. And now I can see it. 1 over cosine is secant. Okay? Please take practice. Tomorrow we're even going to factor in the middle of these with words. Factoring with words. I think we've done it before. All right, one more problem and we're done. One more. Number 11. I really had to skip around on my toes first period. I was like, oh gosh, this is way harder. I cannot do this all in one day. Last one. Take a second and just look at it on your own. I'm going to do it with you, of course, but I want to give you a chance to kind of look at it and see if you can tell. Yeah. Bishop, what'd you say we do? Yeah. Yeah. This looks crazy. How the heck am I supposed to make this look like that? I don't know. I do. But I'm pretending I don't. But I do know that I can change this guy. That's one thing I can do. Do one thing you know how to do. Sometimes I do one thing and I still have no idea what I'm doing. And I have to switch gears. Maybe there's something I missed. Okay? But I'm trying to give you the first things to look for. Okay. So I changed cosecant to 1 over sine. Anybody see something we can do? Cancel the signs, right? We're allowed to because that's multiplied. Just within that fraction we're allowed to. You're left with 1 minus sine squared x. Keep your eye on the prize. Any idea? That's one of your Pythagorean identities. Okay? That is cosine squared x, right? I told you these are going to pop up a lot. And the way we remember them is the squareds with the 1s, the pluses, the minuses. That does equal. Okay, so if you can memorize this one, you should all be able to say, oh, if I get this guy by itself, I would just subtract cosine, right? If I wanted to get him by himself. Or if I wanted to get that one by itself, I would subtract whatever order I just said it in, okay? But you should be able to rearrange this 2 other ways so that you can see that, okay? That's it. Yeah. On this last part? Okay, so do you remember this Pythagorean identity here? Okay, so if I isolated the cosine squared, okay? Anyone think it's fun? Arbor, did you think it was fun? Yeah. Ash, fun? Yeah. I liked it. I know you did. Good job. You and Deshaya? I don't know. She doesn't seem to share your enthusiasm. Okay. If you are still watching this video, I cut off in the beginning. I went over just the reciprocal identities, which I've taught before, and the quotient identities. Okay. And then you jumped in at the Pythagorean.